Have you ever wondered how far a human-made object can travel once it escapes the pull of every planet we know? Voyager 1 is already beyond our solar system, moving through a region where sunlight fades and space begins to behave differently. With each passing year, it drifts farther into a place no probe has ever explored, carrying the faint signal of a world it left behind decades ago. If this kind of quiet journey helps you unwind, a gentle like and subscribe supports the peaceful space we're building here at Fall Asleep with Science. Now, let's follow Voyager 1 and see just how far, far away can truly go. Long before this small traveler slipped into the darkness between the stars, it was only a sketch on paper and a quiet hope in human minds. In the late 1970s, when television screens glowed in living rooms and early computers hummed softly, humanity prepared one of its boldest gestures. We decided to send a pair of fragile machines away from home and let them go farther and farther, until the familiar planets became memories in their cameras and faint whispers in their data. They were called the Voyager spacecraft, twins born from the same dream. Voyager 1 and Voyager 2 were not huge or imposing. They were frames of metal and wire, with a wide dish for listening and speaking, and long arms holding instruments that could sense magnetic fields, measure particles of light, and take photographs of worlds no one had seen up close before. They were built as extensions of our senses, so that Earth could feel what lay beyond its warm inner circle. Bolted to each of them was something softer than any sensor, a golden record, a small circle of metal engraved with sounds and images from our world. Waves folding on a shore, a child laughing, greetings in many languages, music that had filled both concert halls and quiet kitchens. It was a letter without a known address, tossed gently into a cosmic ocean. If anyone, or anything, ever found it, they would hear that around a modest yellow star, there had been a species that cared enough to say, "This is who we were." But the path of our wandering machines does not end with the last familiar planet. Their story draws us into a wider darkness, where new worlds wait. Far beyond the inner planets, past the orbits of the great gas giants, the sunlight weakens and the warmth of home fades. Out there, in the dim edges of our solar neighborhood, lies a small, cold world that once held a place in our school books as the 9th planet, Pluto. For a long time, Pluto was only a faint point in telescopes, a pale ember that hardly seemed to move at all. We traced its orbit and imagined a lonely, frozen sphere at the edge of everything. Much later, another spacecraft followed the path suggested by the Voyagers and went to meet it. That craft, called New Horizons, slipped past Pluto at great speed, and through its steady eyes we finally saw this world clearly. What appeared was quietly astonishing. Pluto was not a dull lump of ice, but a landscape with character. Mountains of frozen water rose like jagged blue shadows. Broad plains of frozen nitrogen stretched smooth and pale, like a sea paused in mid-wave. Near the equator, a light region shaped roughly like a heart and called Tombow Regio spread across the surface, making this distant world feel strangely familiar, as if it were holding out a symbol we might recognize. In that far, thin light, Pluto became more than a number in a table of orbits. It reminded us that even in the coldest places, landscapes can move and change. Ice can creep and flow. A world can quietly rearrange itself over time without a sound. Pluto's soft heart and shimmering glaciers asked us to reconsider what small, distant worlds might be capable of. And beyond Pluto, further into the dim, there are hints of something more. Astronomers noticed that some of the small icy bodies beyond Neptune moved in odd ways. Their orbits were stretched and tilted, as if an unseen hand were tugging at them from the dark. From those clues, an idea emerged. Perhaps there is another world out there, a hidden giant moving slowly at the edge of the sun's influence. People began to call it Planet 9, not as a certainty, but as a possibility. If it exists, it is too faint and too far for us to see easily with today's telescopes. It would be a frozen planet taking thousands of years to circle the sun once. Its presence felt more through the way it bends the paths of others than through any light it reflects. Our solar system, then, may still not be fully mapped. We live in a neighborhood where some of the houses at the edge could still be dark and unnamed. The Voyagers, sailing outward, and missions like New Horizons, flying past Pluto, remind us that the story is not finished. There may yet be a quiet, massive world tracing a long, slow path in the dark, waiting for our patience and our instruments to catch up. To see how we reached the point where such questions could even be asked, we can look back to a hot season many decades ago, when all of this was still only potential. In the sweltering summer of 1977, while people on Earth wiped sweat from their brows and went about their ordinary days, something unusual was aligning above their heads. The great planets of the outer solar system were taking up special positions, forming a configuration that appears only once every 176 years. It was as if Jupiter, Saturn, Uranus, and Neptune were stepping into a loose line, creating a curving corridor that a visitor from Earth could follow. This rare arrangement offered a gift, a chance to send a spacecraft on a grand tour, using the gravity of one planet to fling it toward the next. Each encounter would borrow a little energy from the planet's motion and give it to the probe, allowing it to go farther without carrying impossible loads of fuel. Engineers and scientists saw this opportunity and began to plan in careful detail. They imagined two spacecraft leaving Earth, swinging first by Jupiter, then Saturn, and perhaps even continuing farther, peeling back the mysteries of each giant in turn. This technique, called a gravity assist, turned the planets into stepping stones, helping small machines built by human hands climb out of the sun's grasp. To make that vision real, the Voyagers were designed with stubborn care. They were fitted with cameras that could capture the storms of Jupiter, instruments that could sense magnetic fields around Saturn, detectors that could feel charged particles rushing in the solar wind. Every piece of equipment was chosen so that each brief flyby would matter. Once a spacecraft passed a world, it would not return. There would be only a single chance to look and listen. The road to the launch pad was not gentle. Budgets shrank and stretched. Some voices wondered if the mission was too bold or too uncertain. The deep space environment would be cold, soaked in radiation, and utterly empty of help. Every system on the spacecraft had to be tested again and again to prove it could keep working long after launch day vanished from memory. Yet slowly, the pieces came together. The dish antenna was mounted, instruments were wired in. The golden record, with its library of human sounds, was attached like a charm. People who had spent years on the mission watched as their creations were rolled out under the open sky toward the rockets that would lift them beyond cloud and weather. When launch finally came, the moment was both thunderous and fragile. A countdown, a burst of flame at the base of the rocket, a roar as it climbed through thick air, leaving a bright trail that thinned and vanished into blue. With liftoff, the Voyagers left Earth forever. They carried no crew and no living passengers, yet, in a gentle way, everyone went with them. The questions and quiet hopes of a whole planet rode on those small, humming frames. As the months passed, and the spacecraft slipped beyond the orbit of Mars and through the loose stones of the asteroid belt, another presence grew on their horizon: Jupiter, the largest planet in our system, a globe of cloud and storm whose gravity shapes the paths of many smaller bodies. No probe had ever seen Jupiter so closely. As the Voyagers approached, they turned their cameras and instruments toward the gas giant and began to send back images and measurements. On Earth, screens filled with new views, bands of cloud wrapped around the planet, storms blossoming and fading, fine eddies in its atmosphere. The Great Red Spot, a storm larger than Earth, came into sharp focus, its edges frayed and curled. Alongside these familiar features, quiet surprises emerged. The photopolarimeter, an instrument designed to study how light scatters from the planet and its surroundings, helped reveal that Jupiter is circled by a thin, ghostly ring. For a long time, rings had seemed like Saturn's unique adornment. Now Jupiter, too, was seen to wear a fragile halo of dust and tiny particles. Jupiter's moons also changed from points of light into full worlds. One of them, Io, drew special attention. Voyager's cameras did not find a calm, frozen surface there. They saw a mottled, sulfur-stained landscape marked by patches and dark spots. Watching closely, scientists saw plumes rising high above the surface, fountains of material thrown into space. Io was volcanically active. Its face was being reshaped by eruptions and flows. This was the first time active volcanoes had been seen beyond Earth. Io turned out to be the most volcanically active body in the solar system. Its crust, a restless skin over a heated interior, stirred and squeezed by Jupiter's powerful gravity. Leaving Jupiter behind, the Voyagers continued toward Saturn. Slowly, the pale world surrounded by a bright band grew in their view, resolving into a planet circled by one of the most delicate and beautiful structures in the solar system: Saturn's rings. Through the spacecraft cameras, the rings changed from a single line to a broad disk made of countless icy fragments, each one circling in a careful dance. Sunlight traced across them, turning them into bands of brightness and shade. The radio instruments listened to signals as they passed through the rings and returned, revealing that the rings were full of structure: thin gaps, sharp edges, and braided regions where particles seemed to weave in and out like strands in a rope. Some patterns could be linked to the tugs of small moons nearby. Others remain puzzles that scientists still think about. And then there was Titan, Saturn's largest moon, wrapped in its own mystery. Titan's thick, hazy atmosphere hid its surface from view. To the cameras, it appeared as a soft, orange globe with no clear markings. Yet other instruments could taste the air and hinted at something remarkable. Titan's atmosphere was rich in complex organic molecules, the carbon-bearing ingredients that, under the right conditions, can build more intricate structures. The data suggested that Titan's surface might not be dry, but shaped by liquids far colder than any ocean on Earth. There could be lakes or seas made of liquid hydrocarbons, and a slow, alien kind of weather moving those liquids through cycles of rain and mist. In those brief, passing measurements, Titan began to look less like a distant, featureless moon, and more like a complex world, with its own rhythms and chemistry, sparking curiosity and speculation about the possibility of life on it. As their time in the Saturn system drew to a close, and the Voyagers drifted away from that warm familiarity, they carried with them more than measurements and photographs. They carried a new kind of confidence, a quiet knowing that even the coldest corners of the solar system might hold their own astonishing stories. The encounters with Jupiter, Saturn, and haunting moons like Titan had opened a doorway, revealing that beyond the great gas giants lay worlds stranger and more delicate than we had ever imagined. And Voyager 2 was the one destined to wander farther still, into regions no human-made object had yet seen. In those distant outer reaches, where sunlight thins until it is little more than a pale whisper, Voyager 2 set its course toward Uranus, an ice giant that had been, until then, hardly more than a faint blue smudge in Earth's telescopes. When the spacecraft arrived in the quiet days of January of 1986, humanity glimpsed Uranus properly for the first time. From far away, Uranus looked almost serene, a smooth sphere painted in a soft, icy blue. But beneath that calm surface lay puzzles that had lingered for decades. Uranus is tilted dramatically, its axis lying nearly sideways, almost parallel to the plane of the solar system. This means its poles take turns spending decades in sunlight and decades in darkness. Such an extreme orientation shapes the way its atmosphere moves, creating seasons so long and strange that they barely resemble the rhythms we know on Earth. As Voyager 2 approached, its narrow-angle camera and other sensitive instruments began to tease details out of what once seemed uniform. Faint bands of cloud, subtle motions in the atmosphere, and a set of delicate rings that had been nearly invisible from Earth. These rings were thin and quietly beautiful, narrow threads of material circling the tilted world. One of the most surprising discoveries came from the spacecraft's magnetometers. They revealed that Uranus's magnetic field did not align neatly with its rotation, nor did it sit centered within the planet. Instead, it was tilted and offset, like a lantern held loosely at an angle. This odd geometry hinted at a layered and shifting interior, perhaps oceans of icy, slushy materials or deep, complex currents moving beneath the surface. Then, with its brief visit complete, Voyager 2 pressed on toward its next lonely destination, Neptune, the most distant of the known planets at the time. When the spacecraft arrived in August of 1989, Neptune transformed from a cold, distant mystery into a living world. Instead of the still, icy quiet many had expected, Neptune displayed restless activity. There, near its deep blue equator, Voyager 2 found the great dark spot, a storm as large as Earth, swirling within a turbulent atmosphere, whipped by some of the fastest winds in the solar system. These winds, moving faster than the speed of sound on Earth, carved and stretched cloud formations into long, delicate streaks. Neptune also carried faint rings of its own, subtle arcs that Voyager's instruments captured with patient observation. Within those rings, patterns and clumps whispered of gravitational tugs from small nearby moons. Among Neptune's family of moons, Triton stood apart, a world that did not orbit in the usual forward direction, but instead circled Neptune backward, as if moving against the system's natural current. This retrograde orbit suggested Triton had once been something else entirely, perhaps an object captured long ago. When Voyager 2's camera looked closer, Triton revealed a landscape both frozen and strangely active. The images showed geysers of nitrogen gas and fine dust erupting from the surface, rising in thin, dark plumes and drifting across the icy plains. These geysers hinted that beneath Triton's frigid crust, heat still stirred a faint, lingering fire within an otherwise silent world. With Uranus and Neptune behind it, Voyager 2 had completed the grand tour no spacecraft would repeat for lifetimes. These brief, precious visits offered a treasure of details that continues to shape our understanding of ice giants and distant moons. Even now, decades later, scientists still return to the measurements gathered during those short encounters, finding new meaning in the data. But as the spacecraft moved farther and farther from the sun, another challenge emerged. Energy was limited. Not every instrument could remain awake forever. Mission controllers had to make thoughtful choices about which systems to keep alive. Gradually, non-essential instruments were powered down one by one, allowing the most important sensors to continue their slow, patient watching. Among the systems scheduled for permanent shutdown was Voyager 1's camera. It had taken thousands of photographs: storms on Jupiter, the shimmering rings of Saturn, the soft haze of Titan. Its work was nearly done. Yet before powering it off forever, one astronomer, Carl Sagan, offered a gentle suggestion. What if, before the camera fell silent, the spacecraft turned back one last time toward the place it had come from? A final portrait of Earth, not as a grand, dominating world, but as it truly appears from the edge of the solar system, tiny, faint, and fragile. The idea was simple, almost poetic, and mission controllers agreed. So, on a quiet day, in February of 1990, Voyager 1 slowly warmed the heaters around its camera. It took hours for the instrument to reach operating temperature in the cold vacuum of deep space. Then, over the course of 3 careful hours, the spacecraft captured a series of images from roughly 4 billion miles away, a distance so extreme that Earth did not appear as a shape at all, but as a single pale speck of scattered sunlight. That tiny point, suspended in a shaft of brightness, became known as the pale blue dot. In that little shimmer, the entire human story lived: every joy, every sorrow, every person who had ever breathed. The image called to mind not triumph, but humility, and a kind of shared tenderness for the only home our species has ever known. After that final look back, the Voyagers continued onward, leaving the planets behind. Their paths carried them into regions where no probe had traveled, into the space beyond the sun's protective bubble. This transition marked something extraordinary. The first time anything built by human hands had ventured into true interstellar space. To understand the significance of that boundary, it helps to imagine the sun not just as a star, but as a presence that breathes. From its surface flows a constant stream of charged particles, the solar wind rushing outward in all directions. This wind inflates a vast bubble around the sun and its planets, a bubble called the heliosphere. At its outer edge lies the heliopause, a boundary where the inward pressure of interstellar material balances the outward push of the solar wind. It is not a hard border, but a turbulent, shifting region where the sun's influence fades and the larger galaxy begins. Crossing it meant that Voyager 1 and Voyager 2 were no longer sailing through a realm shaped primarily by our star. They were entering the wider sea between the stars, where particles and magnetic fields belonged not to the sun, but to the galaxy itself. It was a quiet milestone, no shock, no sudden change the spacecraft could feel. Yet for us on Earth, it marked a profound moment, a confirmation that a small pair of metal travelers had left home in the truest sense, carrying with them a trace of our curiosity, our questions, and our willingness to wander into the unknown. When Voyager 1 drifted toward the edge of the sun's fading breath in August of 2012, nothing dramatic happened to mark the moment. There were no sparks, no shudder, no sudden shift in its steady flight. But deep inside, its instruments, little boxes of circuitry and sensors, built when computers still filled rooms, it felt a change. The stream of charged particles pouring outward from our star thinned sharply, dropping away as though a warm wind had stopped blowing. And from the far side of that unseen frontier came something new, a rising tide of high-energy cosmic rays, ancient messengers from across the galaxy, brushing against the spacecraft's detectors with a quiet insistence. That simple pattern, a sudden decrease in solar wind particles, a clear increase in cosmic rays, whispered something extraordinary. Voyager 1 had stepped beyond the heliopause, the delicate frontier where the sun's influence wanes and the galaxy's wider forces begin to take hold. For the first time, a human-made object was drifting through interstellar space, moving through an ocean that belongs not to our star, but to all the stars. And still, from that unimaginable distance, the spacecraft spoke to us. Each snippet of data, crossing more than 20 hours of empty darkness before reaching Earth, carried clues about the shape of our cosmic neighborhood. These signals, faint as dust motes drifting through a sunbeam, revealed how the solar wind mixes with the interstellar medium, how magnetic fields twist and fold, how ancient particles wander between stars, how far the sun's protective bubble truly extends. In their own unhurried way, the Voyagers helped us listen to the quiet history of the galaxy. But their journey also awakened something gentler in us, the sense that exploration does not always require urgency or conquest. Sometimes it is enough simply to drift, to listen, to send back the softest impressions of places no living creature has ever touched. Over the decades, the data returned by Voyager 1 and Voyager 2 reshaped our understanding of the outer solar system. They unveiled the delicate layers of planetary atmospheres, the fine structures of faint rings, the surprising heat hidden inside far-flung moons. Their measurements became woven into textbooks, research papers, and the imaginations of scientists who would later design missions of their own. Cassini followed, slipping into Saturn's embrace for more than a decade, exploring its rings and storms, tasting the gases of its atmosphere, and sending a small probe down through Titan's haze to touch its frozen surface. Juno came after, diving through Jupiter's ferocious magnetic field again and again, gathering secrets from the giant's interior. Each mission stood on the shoulders of the Voyagers, reaching deeper because the path had been illuminated before. Now, the scientific community dreams of voyages that have not yet begun missions to Uranus and Neptune, the quiet ice giants that Voyager 2 glimpsed in hurried passing. These worlds wait in the dim outskirts of sunlight, their weather slow and strange, their rings faint, their moons icy and mysterious. A closer look could reveal how such distant planets formed, what storms churn inside them, and how their magnetic fields twist so differently from those of the inner worlds. They may hold answers not only about our solar system's past, but about the countless ice giant exoplanets discovered around distant stars. Yet among all the scientific instruments and discoveries the Voyagers carry, nothing has touched the human spirit quite like the Golden Record. It rests on the side of each spacecraft, a 12-inch disc of gold-plated copper, glimmering faintly in starlight that no human eye will ever see directly. On it are the sounds of earth waves breaking on a rocky shore, a mother's voice, the chirp of birds greeting dawn, the hush of wind moving through leaves. There are songs from many cultures, the formality of Bach and Beethoven, the rhythms of traditional drums, the softness of reed flutes, the harmonies of voices from places far apart and yet bound by the same sky. The record holds images too, mountains dusted with snow, forests dense with life, a newborn's tiny hand curled in sleep, diagrams of DNA's spiraling ladder, and star maps showing our location in the galaxy. It is a portrait of Earth, drawn not in words, but in the universal languages of sound, pattern, and number. Carl Sagan and the team behind the record chose each element with tenderness. They wanted to express not just what humanity knows, but what humanity feels, the beauty we recognize, the curiosity that shapes us, the fragile hope that even the darkest corners of the universe might someday be shared with another mind. On the record's protective cover, engraved in quiet mathematical symbols, are instructions meant for beings we cannot imagine. These markings explain how to play the record, how to decode its sounds, how to understand the images, and where this little messenger began its journey. It is a gesture of trust across time and starlighted distance, a message cast into a cosmic sea where it may float for billions of years. Meanwhile, Voyager 1 and Voyager 2 continue their slow departures. With each passing hour, they drift farther away, their signals thinning as distance grows. It now takes more than 22 hours for a radio whisper from Voyager 1 to reach Earth. 22 hours of crossing a silence so large it barely seems possible. To catch those whispers, Earth relies on the Deep Space Network, great radio antennas placed in lonely deserts and quiet hillsides across the planet. These dishes, enormous and patient, tilt their wide, metal faces skyward, listening for the faintest thread of a message. When the Voyagers speak, the Deep Space Network hears them not as words or pictures, but as shimmering ripples in the radio spectrum, soft pulses that must be amplified, cleaned, and interpreted with care. Every time a signal arrives, it is a triumph of engineering that began long before the spacecraft left Earth. The Voyagers were designed to last only 5 years, long enough to sweep past Jupiter and Saturn. Yet, through robust construction, redundant systems, and careful stewardship, they have lived far beyond their expected span. At the heart of their longevity lies the radioisotope thermoelectric generators, RTGs, that keep them warm and powered. These units convert the heat from the decay of plutonium-238 into electricity, a slow, steady process that has kept the spacecraft alive for decades. But the heat diminishes over time, and with it, the available power. Every year, mission controllers must choose which instruments to keep running and which to let go. It is a gentle triage, guided by both scientific value and the quiet wish to hear the spacecraft's voice for as long as possible. Eventually, heaters will grow too weak, instruments will fall silent, and even the main transmitter will no longer have enough energy to speak across the void. Yet even after their radio voices fade, the Voyagers will not stop. Momentum alone will carry them forward, slipping between the stars like tiny seeds cast into endless soil. They may pass within light years of other suns, gliding through regions no human will ever see. They may outlast the Earth itself, outlast our languages, our cities, our distant descendants, and somewhere in that vast dark, long after the last human ear has heard from them, the golden records will remain intact, silent, waiting, patient. Each one, a lantern carrying a memory of a small blue world that once shone with oceans, forests, music, and dreams. Each one a reminder that our species, fragile and temporary as we are, once reached outward with open hands, hoping to be understood. In the end, the Voyager's true frontier is not measured by distance. It is measured by how far a message can travel, how long a gesture can last, and how deeply curiosity can anchor itself into the heart of a civilization. And even as these little explorers fade into the quiet between the stars, their legacy glows softly behind them, like the afterimage of a spark carried on a night wind, a testament to human wonder, and to our unquenchable desire to explore the unknown, far beyond the paths now traced by the Voyagers. In the same great darkness, but closer to the sun's fading light, another story waits in the cold. Out there, past the orbit of Neptune, the solar system thins into a realm of ice and shadow. Grains of rock and frozen worlds drift in slow, wide circles, and among them moves a small body that has captured human curiosity for almost a century. This is Pluto. For a long time, Pluto lived mostly in our imagination. It was spoken of in classrooms as the ninth planet, drawn as a tiny dot on the far edge of the diagram, a distant neighbor no one had ever truly seen. Children traced its orbit with the tips of their fingers on glossy textbook pages, following that long, stretched path around the sun and wondering what it might feel like to stand on such a faraway shore. Later, when astronomers agreed to place it in a different category and call it a dwarf planet, it did not become less mysterious. It occupied a space between ideas, too small and icy to match the giant planets, yet too structured and complex to be dismissed as just another rock. The change in its status sparked conversations both among scientists and in living rooms. Some people felt a pang of loss, as if a familiar member of the planetary family had been gently moved to a different table. Others welcomed the new classification as a sign that our understanding of the solar system was becoming more precise. Underneath the emotions, though, Pluto itself did not change. It continued its slow, silent journey, indifferent to our labels, gliding along its path at the edge of the sun's domain. Seen from Earth with even the most powerful telescopes, Pluto was for decades nothing more than a blurry speck of light, a faint, trembling point at the very edge of our vision. It followed a stretched, tilted orbit, gliding through the dim outer regions where sunlight is weak and the night is nearly complete. From that distance, it was easy to imagine Pluto as a simple, frozen relic, a leftover shard from the solar system's early days, holding its secrets in silence. The story of Pluto, though, began long before spacecraft ever went there. In the early years of the 20th century, some astronomers became convinced that there was another large planet lurking beyond Neptune, a hidden body they called Planet X. They were not hunting only for a new name to add to a list. They were trying to explain subtle irregularities in the orbits of the known planets, tiny deviations that hinted at the tug of an unseen mass far out in the dark. At Lowell Observatory in Flagstaff, Arizona, a young astronomer named Clyde Tombaugh took on the patient work of searching for this ghostly world. Night after night, he aimed a telescope at carefully chosen patches of sky, capturing images on photographic plates. Each plate froze a field of stars in time. Later, under the soft light of the observatory, he would compare pairs of plates taken days apart, using a machine that blinked them back and forth. Among thousands of steady pinpricks, he looked for anything that moved. It was slow, eye-straining work, the kind of task that demands both endurance and a very quiet kind of faith. Then, on a February night in 1930, the patience paid off. On one pair of plates, a tiny point shifted its position against the fixed background of stars. It was small, faint, and stubbornly unremarkable at first glance, but it moved, and that made all the difference. Clyde Tombaugh had found Pluto, a distant world that would stretch the map of our solar system and capture the public imagination. Pluto was given the name of the Roman god of the underworld, a fitting title for a world buried in darkness. For decades afterward, though, it remained more symbol than place. We knew its orbit and its approximate size, but not its face. The outer solar system was simply too far for clear images. It was like knowing a neighbor's address but never having seen their home. Then, in the closing years of the 20th century, a new eye opened in the sky. The Hubble Space Telescope, launched into orbit in 1990, rose above Earth's blurring atmosphere and turned its mirrored gaze toward distant targets. When Hubble looked at Pluto, the view shifted from a single blurred dot to a world with light and dark regions. Subtle variations in brightness and color spread across its tiny disk. These early images were still coarse, like a painting seen from very far away, but they were enough to suggest complexity. Pluto's surface was not uniform. Patches of brighter and darker terrain hinted at ice, frost, perhaps seasonal changes and varied chemistry. The dwarf planet was not a simple frozen ball. It was a place where processes might still be at work, even in the deep cold. For planetary scientists, this was like seeing a curtain lift just enough to reveal a shadow of something intricate behind it. Little by little, interest in Pluto grew. The idea that this distant, dim object might be geologically active or shaped by exotic ices stirred the curiosity of scientists who had already been amazed by the surprises of Io, Europa, Titan, and Triton. An odyssey that began as a blinking speck on a photographic plate was now moving toward something more, a direct encounter. To turn that quiet desire into reality, a new mission had to be imagined. Engineers and scientists proposed a small, fast spacecraft that could race across the solar system and, for a brief moment, pass close enough to Pluto to reveal its face. The spacecraft would have to be light, efficient, and incredibly precise, able to sleep through long stretches of cruise and then wake up exactly when needed. That vision became New Horizons. In January of 2006, at a launch site in Florida, people gathered to watch a slender rocket carry this new traveler into the sky. New Horizons was not large. Its main body was about the size of a grand piano, wrapped in gold-colored insulation and bristling with instruments. Inside were cameras to catch every possible detail, spectrometers to read the fingerprints of light bouncing off ice and rock, dust detectors, and particle sensors to taste the thin environment around Pluto and its moons. When the countdown reached its final words, 5, 4, 3, 2, 1, the rocket engines roared to life. Flames and smoke billowed outward, and the vehicle climbed through the clouds, carrying with it years of planning and the hopes of countless people who had worked late into many nights, adjusting designs, testing hardware, checking and rechecking every line of code. In moments, New Horizons had left the atmosphere behind, becoming a small, silent point racing away from its home world. The journey ahead was immense. To reach Pluto, the spacecraft would need to travel for nearly a decade, crossing more than 3 billion miles of space. It flew past the orbit of Mars, slipped through the asteroid belt, and paid a brief visit to Jupiter, using the giant planet's gravity as a slingshot to gain speed. After that, the mission entered a long, quiet cruise phase, with the spacecraft spending much of its time in a kind of electronic sleep to preserve energy and reduce wear. In that dormancy, it coasted through deep space, its systems monitored from afar, its path gently nudged, when needed, by small bursts from its thrusters. On Earth, teams of engineers periodically woke New Horizons, checking its health and refining its trajectory, making tiny adjustments so that, after all those years, it would arrive at just the right point in space, at just the right time. The timing had to be incredibly precise. Pluto is small and distant, and the spacecraft was moving so fast that a significant error could mean missing the target entirely. Each course correction was like a small, careful touch on the shoulder of a runner mid-stride, guiding it toward a distant finish line no one could see directly. As 2015 approached, anticipation grew. Astronomers, students, and people who simply loved the night sky all watched the calendar creep toward the planned encounter. In observatories, classrooms, and living rooms, people followed the shrinking distance between New Horizons and its icy goal, feeling the strange intimacy of waiting for a machine to reach a world no person would likely touch for many lifetimes. After almost 9 years in flight, New Horizons began to send back its first close-up images. At first they were small and grainy, but each new picture sharpened the view. The world that emerged from the darkness was nothing like the simple ice bowl many had expected. Pluto's surface resolved into mountains, valleys, and broad plains. Towering ice peaks, some as tall as the Rocky Mountains on Earth, rose from the surface, made not of stone, but of frozen water as hard as rock in that distant cold. Between them stretched vast expanses of nitrogen ice, smooth and pale, flowing in slow, glacier-like rivers across the dwarf planet's face. One region quickly drew the world's attention, a vast, bright, plain shaped roughly like a heart. This area, known as Tomball Regio, in honor of Pluto's discoverer, appeared as a smooth, light patch set against darker, more rugged terrain. Across one lobe of this heart lay a feature informally called Sputnik Planitia, a nitrogen ice basin marked by a network of polygonal cells and subtle ridges and pits. These patterns suggested slow, convective motions within the ice itself, as if the frozen surface were gently churning over immense spans of time. Warm from below, just enough to move with near imperceptible grace. The discoveries did not stop there. New Horizons found hints of possible cryovolcanoes, ice volcanoes that might once have oozed slurries of water, ammonia, or other exotic ices instead of molten rock. It saw evidence that Pluto's surface had been reshaped relatively recently in geological terms, meaning that heat from within or from tidal interactions long ago may still be influencing the dwarf planet's crust. Glaciers of nitrogen appeared to creep along valley floors, shaping the land as they moved, leaving behind ripples and flows that told a slow, frozen story. Even Pluto's thin atmosphere, made mostly of nitrogen with traces of methane and other gases, revealed itself in delicate layers of haze, stretching high above the surface. Against the backlighting of the distant sun, these hazes formed soft, blue-tinged shells, stepping upward in gentle tiers. They hinted at processes lifting molecules from the surface, letting them rise, cool, and settle again like a faint, icy breath. All of this pointed to a startling conclusion. Pluto, long thought to be a frozen relic left unchanged since the early days of the solar system, was in many ways still alive. Its surface showed signs of renewal and motion. Its ices flowed. Its plains were not heavily scarred by ancient craters, suggesting that old marks had been smoothed away by ongoing processes. For people watching from Earth, the transformation was profound. A world that had once been nothing more than a dim point had become, almost overnight, a place with character, a world with a bright heart, rugged mountains, flowing glaciers, hazy skies, and perhaps even a complex internal structure. The gap between expectation and reality had been bridged in a single flyby. As New Horizons sped past and continued outward into the Kuiper Belt, it left behind a changed understanding of what small, distant worlds can be. Pluto was no longer a distant curiosity, half real and half imagined at the edge of a textbook diagram. It had become a fully realized place in our mental map of the solar system, full of surprises and quiet beauty, waiting in the deep cold at the frontier of the sun's light. And for all the questions it answered, it was just the beginning of a new chapter in our understanding of the cosmos. Pluto's rugged expanses hold many quiet wonders, but one region draws the eye again and again. Near the center of the bright heart that New Horizons revealed lies Sputnik Planitia, a vast, light-colored plain that forms one lobe of Pluto's heart. From a distance, it looks like a smooth, frozen lake of pale ice, pressed gently into the surface of the dwarf planet. It is the part of Pluto that almost seems to be looking back at us, a soft shape against a darker background. Up close, it becomes clear that this is not just a pretty outline on a map, but one of the most astonishing geological features in the outer solar system. Sputnik Planitia is an enormous basin, stretching for more than 650 miles from end to end, wide enough to swallow entire countries on Earth. Many scientists believe it was carved long ago by the impact of a large celestial body, a collision powerful enough to scoop out a huge hollow in Pluto's crust and shake the entire world to its core. Such an impact would have released unimaginable energy, sending ripples through the interior and perhaps reshaping Pluto's history from that moment onward. Over time, this hollow filled with ices, mostly frozen nitrogen mixed with carbon monoxide and methane and other exotic compounds, settling like a bright, reflective lake into the sky. The result is a smooth plain that stands in sharp contrast to the darker, more rugged terrain that surrounds it, as if a fresh page had been laid down on top of an older, more battered book. If you look carefully at Sputnik Planitia in the close images from New Horizons, you can see that its surface is not smooth like glass. Instead, it is divided into a patchwork of gently raised polygons, each one roughly the size of a small country on Earth. The boundaries between them are lined with slightly darker ridges and troughs, where ice seems to sink and gather. These are convection cells, slowly overturning blocks of nitrogen ice, rising in the center where they are slightly warmer and sinking at the edges where they cool. The motion is so slow that you would never notice it if you stood there, but over millions of years, the entire plain quietly churns. The process is a bit like watching a lava lamp, but in freezing conditions so extreme that water behaves like rock and nitrogen behaves like a very slow, thick fluid, driven by the faint heat seeping from Pluto's interior. This convection causes the surface of Sputnik Planitia to constantly renew itself over vast spans of time. Old craters are erased as rising ice fills them in from below. Ridges soften, and new patterns emerge where sinking ice drags material downward. In some regions, you can trace the flow of glaciers creeping outward from the basin, carrying ice into the neighboring highlands. This gentle, ceaseless movement shows us that Pluto is not a completely inert relic, frozen solid since the birth of the solar system. Even at this distant frontier, far from the sun's warmth, there is still enough internal energy to rearrange the landscape in slow motion and to keep parts of the surface looking geologically young. Beneath the shining sheet of nitrogen ice, the story may be even more surprising. Measurements of Pluto's gravity field, combined with detailed maps of its shape and rotation, suggest that Sputnik Planitia does not sit above an unusually light region, as one might expect from a giant hole filled with ice. Instead, its mass distribution appears oddly uniform, or even slightly heavier than the surroundings. For a basin that was once a deep cavity, this is puzzling. To explain this, many scientists think there may be a denser layer hidden beneath the basin, possibly a subsurface ocean of liquid water tucked under the icy crust like a concealed sea. In this picture, the impact that created Sputnik Planitia may have thinned Pluto's outer shell, allowing an underlying ocean to bulge upward, closer to the surface. Water, which is denser than the surrounding ice, could then pool beneath the basin, acting as a kind of hidden ballast. Over time, this buried ocean might help keep the depression from rebounding upward and disappearing. It would stabilize the basin in place, even as it slowly evolves. If such an ocean exists, it would not be an open sea under a sky, but a dark, pressurized layer sealed beneath hundreds of miles of ice, isolated from space, yet gently influencing the world above through its weight and its slow movements. The possibility of a subsurface ocean on Pluto links this distant dwarf planet to other intriguing worlds, like Europa and Enceladus, where buried seas may also exist. It suggests that liquid water, kept warm by the leftover heat of formation and the slow decay of radioactive elements, may be a common thread running through very different corners of our solar system. On Pluto, any such ocean would be ancient and deeply hidden, but its presence would still matter. It could shape the surface, affect the way Pluto spins, and perhaps even provide a long-lived environment where chemistry has time to explore all kinds of possibilities. Floating above all of this, Pluto wears a whisper-thin atmosphere, draped over its surface like the lightest of veils. It is composed mostly of nitrogen, with a touch of methane and carbon monoxide, similar in some ways to the gases frozen on the ground below. For years, many scientists expected this atmosphere to hug the surface fairly closely, constrained by the dwarf planet's weak gravity and the fierce cold of the outer solar system. It seemed reasonable to imagine a skim of gas clinging to the ice and fading quickly with height. Instead, when New Horizons flew past, it found that Pluto's atmosphere reaches hundreds of miles above the ground, more extended and more complex than anyone had anticipated. Backlit by the distant sun, this airy shell appeared layered, built from many thin hazes, stacked one above another, like transparent pages in a book. Tiny particles, formed when sunlight breaks apart methane and other molecules, and then allows them to recombine into more complex species, drift upward and outward. As they float, they scatter blue light in much the same way Earth's own atmosphere does. In some images, Pluto's sky glows with a soft bluish tint, an almost shocking echo of home, against a landscape of nitrogen, ice, and shadowed craters. The behavior of this atmosphere is closely tied to Pluto's unusual orbit and tilt. Pluto takes about 248 Earth years to complete a single path around the Sunday. Its orbit is highly elongated, carrying it much closer to the Sun at perihelion than at its farthest point, aphelion. On top of that, Pluto's axis is tipped by roughly 120 degrees, so that its poles can spend decade after decade either leaning toward the weak sunlight or turned almost completely away from it. This combination gives Pluto a seasonal cycle that is nothing like the gentle yearly rhythm we experience on Earth. Because of this stretched orbit and extreme tilt, each season on Pluto can last for many tens of Earth years. When parts of the surface tilt into the feeble sunlight near perihelion, that light, though faint, is just strong enough to set a subtle transformation in motion. In regions facing the sun, surface ices made of nitrogen, methane, and carbon monoxide begin to sublimate. Instead of melting into liquid, they change directly from solid to gas, lifting off the ground and joining the atmosphere as invisible vapor. This outgassing thickens the air, raising the surface pressure and allowing the atmosphere to swell upward, expanding to heights of hundreds of kilometers above the surface. The expansion is not uniform. Pluto's varied topography and patchwork of icy compositions mean that some areas warm and sublimate more readily than others. Valleys may trap cold air, bright icy plains may reflect more sunlight, darker regions may absorb heat. All of this helps shape subtle breezes and currents in the thin air, creating a climate system that is delicate, yet surprisingly complex for such a small and distant world. As Pluto slowly moves away from the Sun again and slips toward the colder stretches of its orbit, the process reverses. The gases that once rose from the surface begin to cool and condense, falling back as a fine frost or snow of nitrogen, methane, and carbon monoxide. Over time, these snows can build up layers of seasonal ice, shifting the brightness and texture of the terrain from one long season to the next. The atmosphere thins, shrinking closer to the ground, and parts of it may all but collapse during the coldest phases of Pluto's long year, leaving only a faint, residual film of gas above some regions. This grand, slow exchange between ice and vapor, unfolding over centuries, paints Pluto as a world in motion rather than a static, frozen wasteland. Its plains are reshaped by flowing ices. Its basins may be supported by hidden oceans. Its sky breathes in and out across the ages as ices evaporate and fall again as snow. Even at the edge of the Sun's domain, change is constant, just stretched out over timescales longer than any human life. Another striking aspect of Pluto's atmosphere is how easily it can escape. Unlike the giant planets, which hold tight to their gases with deep gravity wells and, in some cases, strong magnetic fields, Pluto's pull is gentle and its shield is thin. The molecules in its upper atmosphere have enough energy, especially when stirred by sunlight and by interactions with the solar wind, to drift away into space. New Horizons found that this escape is not just a quiet leak, but part of a lively and intricate interaction with the solar wind, the steady stream of charged particles blowing outward from the sunday. As these solar wind particles slam into Pluto's escaping gases, they strip electrons away and create a flow of ionized material that is swept downstream, forming an invisible, comet-like tail that stretches away from the sunday. Around Pluto, the interaction between the solar wind and this escaping atmosphere carves out a small region where the flow of particles is diverted, slowed, and reshaped. In this miniature magnetosphere, without a strong intrinsic magnetic field of Pluto's own, the drama of solar and planetary forces is acted out on a tiny, distant stage, far beyond the warmth of the inner worlds. Far out in the cold, where Pluto breathes its thin, escaping air into space and trails a ghostly tail behind it, another presence moves in quiet lockstep nearby. Pluto is not truly alone. Beside it, bound by gravity and time, circles its largest moon, Charon, a companion so important that together they almost behave like a double world. Charon was discovered in the late 1970s, when astronomers studying Pluto noticed that its tiny disk seemed to wobble in a regular rhythm. Careful observation revealed that this was no trick of the telescope, but a sign of another body orbiting close by. What at first looked like a mere satellite turned out, with time and better data, to be a whole world of its own, with a complex history written across its surface. When New Horizons flew through the Pluto system, it turned its cameras toward Charon and saw a landscape that was anything but simple. Great canyons cut across the moon's face, some so long and deep that parts of Earth's Grand Canyon could fit comfortably inside them. These chasms slice through plains and plateaus, as though the moon had once stretched and cracked, opening immense scars that never fully healed. Along their edges, sheer walls fall into shadowed depths, and ridges run for hundreds of miles beneath a sky forever dim. Elsewhere, mountains rise sharply from the surface, their peaks catching the distant sunlight and casting long, cold shadows across surrounding valleys. These are not gentle hills, but hard, broken uplands, hinting at forces that once pushed and pulled the crust from below. The colors on Charon's surface shift from neutral grays to subtle reddish caps near its poles, where strange materials, perhaps processed by sunlight or charged particles, stain the ice. The origins of this dramatic topography likely lie in Charon's internal past. As the moon cooled over millions of years, its interior may have contracted, squeezing the crust and causing it to split open along great faults. In some places, icy material may have welled up from below, building rough highlands. There are hints that cryovolcanic activity, eruptions of slushy water and other ices instead of molten rock, could have resurfaced parts of Charon, smoothing some regions while leaving others torn and rugged. In this way, Charon's face became a patchwork of old and young terrains, stitched together by tectonic stretching and cooling. What truly sets Pluto and Charon apart, though, is their shared dance. Many moons circle their planets like small companions, looping around a massive central body that barely shifts in response. Pluto and Charon are different. They are locked together in a gravitational partnership so intimate that both of them always show the same face to each other. This mutual tidal locking means that if you stood on one side of Pluto, Charon would hang in the same place in the sky, never rising or setting. On Charon's near side, Pluto would do the same, a fixed giant hovering low, turning slowly but never leaving its place. Their orbits tell another part of the story. Pluto and Charon do not circle one another around the center of Pluto alone. Instead, they both orbit a point in the empty space between them, the system's barycenter. This point lies outside Pluto's surface, which makes their arrangement feel less like a simple planet-moon system and more like a binary pair, two bodies in partnership. This unusual configuration gently blurs the usual definitions that separate planets from moons. In a way, Pluto and Charon are co-travelers, bound together as they glide through the Kuiper Belt. Around them, a handful of smaller moons, Styx, Nix, Kerberos, and Hydra, trace out more complex paths. These tiny, irregular bodies are influenced not only by Pluto's gravity, but also by Charon's steady pull. Their orbits are shaped by resonances and subtle nudges that keep the entire system in a delicate balance. The presence of Charon helps stabilize this miniature many-body dance, offering a living example of how gravity can sculpt harmony from chaos. By studying the motions of these little moons, scientists gain insight into how similar gravitational interactions might shape other systems across the universe, from exoplanet families to asteroid clusters. All of this takes place in a much broader setting. The Kuiper Belt, the wide, dim band of icy bodies that stretches beyond Neptune's orbit like a distant shoreline of the solar system. Pluto, with its complex terrain and active atmosphere, stands among countless other objects that never grew large enough to become full-fledged planets. For a long time, these Kuiper Belt objects existed only as faint points in telescopes, their existence hinted at by orbital calculations and occasional discoveries of new icy worlds. Now we know that Pluto has company. Dwarf planets like Haumea and Makemake, along with many smaller, lesser-known bodies, share this region. Each one carries a slightly different mix of ice and rock, and each follows its own elongated path around the Sunday. Together, they form a kind of fossil record of the early solar system, a frozen archive preserving materials and structures from the time when the planets were first assembling. Unlike the planets closer to the Sun, many Kuiper Belt objects have remained largely untouched by intense heat. Their ices have not melted and re-solidified in the same dramatic ways that shaped worlds nearer the center. Their compositions, mixtures of water ice, nitrogen, methane, and darker, carbon-rich materials, offer hints about the ingredients that once filled the protoplanetary disk. By studying Pluto, Charon, and their neighbors, scientists can look back in time and see what raw materials were available when the giant planets and rocky inner worlds were forming. The Kuiper Belt also plays a quiet but important role in the overall dynamics of the outer solar system. Objects there can be nudged by the gravity of Neptune and the other giant planets, slowly shifting their orbits. Some may someday be scattered inward as comets, bringing with them fresh ices and complex molecules to the inner realms. In this way, even the smallest chunks of ice far beyond Neptune may have long-term effects on the environment of the planets, including Earth. New Horizons, after its dramatic flyby of Pluto, did not fall asleep or turn back. Its journey continued deeper into the Kuiper Belt, seeking another target that could be reached with the fuel and time still available. That next destination was a small object now known as Arakoth, a name that means sky in the language of the Powhatan people. When the spacecraft met it on the first day of the year 2019, it provided humanity with its first close look at one of the most primitive building blocks of the solar system. Arakoth appeared in the images as a gentle, fused pair of lobes, resembling a snowman shaped from reddish clay. Unlike worlds sculpted by strong gravity into spheres, Arakoth's weak gravity allowed it to remain elongated and lumpy, a clue that it had never been heated or squeezed into a more regular form. Its surface was relatively smooth and unscarred, suggesting a quiet history with few violent impacts. The two lobes, a larger one and a smaller one, had come together so gently that they did not shatter, but merged, preserving their shapes like two pebbles pressed softly into the same hand. Closer analysis suggested that the larger lobe, sometimes called Wenu, was not a single solid block, but a cluster of smaller pieces, chunks several miles across, that had gathered together in a loose, cohesive structure. Instead of being sculpted by high-speed collisions, this body seemed to have grown by slow accumulation, with bits of material drifting together at speeds of only a few feet per second. It is like imagining pebbles floating in syrup, gradually touching and sticking, rather than crashing and breaking. This picture challenges the older view that planetesimals, the seeds of planets, formed mostly through high-velocity impacts. Instead, Arakoth suggests a gentler story for at least some regions of the early solar system. A cloud of particles gradually clumping together, losing angular momentum step by step as collisions bleed off motion, and eventually settling into a single, unified object. Over time, those small, softly assembled bodies could gather into larger and larger ones, building up the architecture of the planets themselves. By visiting Arakoth, New Horizons gave us a glimpse of the solar system's childhood, preserved in deep freeze. The way its lobes are joined, the smoothness of its surface, and the subtle variations in color all point toward a cosmos that, in its earliest days, was not only violent and chaotic, but also capable of deep patience. On these small scales, gravity and time work together not as wrecking balls, but as careful hands, nudging and gathering, letting matter settle into new forms. In this quiet corner of the Kuiper Belt, far beyond the warmth of the inner worlds, Arakoth stands as a reminder that the planets we know began as tiny, fragile things. Its very shape holds the memory of slow mergers and gentle contacts, forming an image of a patient cosmos where the building blocks of planets come together in a long, unhurried cycle of gravity and time. Beyond the quiet stillness of Arakoth's twin-lobed form, where New Horizons left its silent fingerprints on the ancient dust of the Kuiper Belt, new dreams have begun to gather. They rise not in haste, but in that thoughtful, lingering way ideas do when people look at something small and distant and feel a pull, gentle but impossible to ignore. The frontier never stays still for long. Even in the cold outskirts of the solar system, imagination warms the air. Scientists and engineers, carrying the glow of past missions in their memories, have started sketching the next possibilities. Tiny shapes on paper, computer models, stray notes on whiteboards that hint at futures not yet built. Among these whispers is one idea that returns again and again: an orbiter, a spacecraft that would not simply pass by Pluto as New Horizons did, but stay there, circling and watching. Such a craft could map Pluto's surface in exquisite detail, tracing the fine ridges along nitrogen plains, following the shifting patterns of haze in its atmosphere, peering into the long shadowed regions wrapped in near-permanent night by Pluto's extreme tilt. It could observe the tiny moons dancing around the Pluto-Charon pair, catching their subtle wobbles and drift. With time, it could watch how frost appears and vanishes across Pluto's face through the decades of its long, slow seasons. To make such an orbiter possible, engineers imagine borrowing a little of Cassini's grace, letting Charon's gravity act as a sling, a pivot, a partner. By looping between Pluto and its moon again and again, the spacecraft could weave a complicated ballet around the system, changing altitude, angle, and vantage point as needed. It would be a mission measured not in a single snapshot but in years of quiet observation, a watchful companion to a pair of worlds that rarely change quickly enough to reveal themselves in one glance. Electric propulsion, the same whispering engines that carried NASA's Dawn spacecraft across the asteroid belt, might help such an orbiter drift gently from one orbital path to another. If all went well, it might even wander beyond the Pluto-Charon system after its long stay, continuing the voyage into new corners of the Kuiper Belt. And then, further out on the horizon of imagination, lie even bolder concepts. Engineers have begun studying propulsion systems unlike anything flown before. Ideas like direct fusion drives, where the heat of controlled fusion could hurl a spacecraft outward with unprecedented speed. One proposal, explored within NASA's Innovative Advanced Concepts program, describes a fusion-powered orbiter and lander that could reach Pluto in only 4 years. Not the 9.5 years New Horizons needed, nor the decades required by older probes, but 4 swift turns of Earth around the Sunday. A spacecraft of roughly 1,000 kilograms, dense with instruments, strong enough to land, patient enough to orbit, could arrive while the people who designed it still remembered the earliest sketches on their desks. Whether these futuristic machines ever launch or remain beautiful dreams, their existence shows how the outer solar system has captured us. Each new technology shortens the gap between thought and destination, drawing distant worlds a little closer, softening the border between what is reachable and what is still only imagined. As we drift through these possibilities, our understanding of the cosmos evolves. Pluto's story, from its discovery to its reclassification and beyond, reminds us how dynamic science truly is. Every time we think we have settled on neat definitions, a new observation nudges us gently toward revision. The universe asks us to stay flexible, curious, open. Pluto's long, looping path around the Sun deepens this reminder. Its orbit lasts 248 Earth years, and during that time it sometimes appears to cross inside Neptune's distance from the Sunday. For a brief part of its journey, Pluto is, in a purely visual sense, closer. But this crossing does not carry danger. The two worlds are caught in a quiet, protective rhythm, a mutual orbital resonance that keeps them safely apart. While their orbits may overlap on paper, their positions never clash in reality. Pluto and Neptune move like dancers who step across the same stage but never collide, guided by an invisible choreography written in gravity. Still, this unusual orbit fed decades of debate over Pluto's status. In 2006, when the International Astronomical Union refined the definition of a planet, Pluto found itself placed in a new category. It joined the growing family of dwarf planets, objects that are round, substantial, and interesting, but that share their orbital zones with others. This reclassification sparked conversations everywhere, in classrooms, on news shows, around dinner tables. Some felt sorrow, some relief, some curiosity. But beneath the debate, Pluto remained exactly what it had always been: a complex, icy world in a crowded and distant neighborhood. That neighborhood is the Kuiper Belt, a sprawling collection of icy bodies that stretches far beyond Neptune. It is a place where categories blur, where objects are neither planets nor mere rocks, where moons and dwarf planets and fragments of ancient material drift together in quiet fellowship. Studying Pluto and its relatives forces us to think more broadly about what a world can be. Some have thin atmospheres. Some are irregular clusters of ice. Some may hide oceans beneath crusts of ancient frost. Diversity, not uniformity, is the rule. Every piece of this region, from the smallest frozen shard to the largest dwarf planet, carries a story from the early solar system. These objects were built from the same swirling cloud of dust and ice that gave birth to Jupiter's storms, Earth's oceans, and the rings of Saturn. They are untouched archives, tiny time capsules waiting in the cold. As we stand at the threshold of new exploration, Pluto's legacy helps guide our way. New Horizons showed us that even the faintest points of light can hold entire worlds of surprise. Arakoth taught us that planetary building blocks need not smash together violently. Sometimes they gather gently, shaped by patience more than chaos. Each new mission adds another thread, weaving a tapestry that stretches from the sun's warmth to the farthest dim glow at the edge of the heliosphere. And yet, even with all we now know, the outer solar system holds secrets not yet revealed. Beyond Neptune's bright presence, and beyond Pluto's quiet heart, astronomers have noticed something stirring in the paths of the icy worlds that orbit far from the Sunday. Their orbits are stretched and clustered in ways that seem unlikely to be random, as though some distant, unseen hand is gently tugging at them. In the vast silence past the Kuiper Belt, where the sunlight is only a whisper and the dark has its own weight, something may be hiding. Not a ghost or a myth, but a gravitational presence, subtle, constant, and large. This hypothetical world is known to us only by the name Planet 9. No telescope has captured its light. No spacecraft has stumbled across its path. Instead, its potential existence is deduced from clues left behind by trans-Neptunian objects whose orbits twist in peculiar ways. They loop and tilt as though influenced by a massive body far beyond Pluto, a body that has yet to reveal itself. Could there be a rogue planet out there alone, enormous, wandering through the cold? A world shrouded in darkness, exerting its influence from afar, a world that defies our expectations and stretches the borders of what we believe belongs to the solar system? Some astronomers think so. Others remain skeptical, but the search continues, quiet, patient, and full of wonder. With each new observation, with each model refined, the picture sharpens by the faintest margin. We gather clues from the edges of the sun's realm, piecing together hints scattered across the outer dark in the hope of finding a world that so far has eluded every eye. And so we listen, we watch, and we wait, wondering what secrets may lie just beyond the reach of our light. In the early years of the 1990s, just as new telescopes and better detectors were beginning to sharpen our view of the night, the outer reaches of the solar system quietly started to give up a few of their secrets. Astronomers who had long suspected that Pluto might not be alone out there began to find companions. Small, icy bodies drifting far beyond Neptune, following elongated paths through the deep cold. Piece by piece, these discoveries revealed a vast, previously unseen region, a broad band of frozen worlds that we now call the Kuiper Belt. Before this, the outer edge of the planetary map had seemed relatively simple. There were the familiar 8 major planets, and beyond them, Pluto, the shy and distant 9th, tracing its tilted, stretched orbit like a solitary wanderer. But as more and more icy objects appeared in the data, that picture began to change. Pluto was no longer a lone sentinel at the boundary. It was part of a crowd. Some of these new Kuiper Belt objects were small, little more than icy fragments. Others were surprisingly large, rivaling Pluto in size, or even surpassing it. Names like Eris entered the conversation, bringing with them a fundamental question. If Pluto is a planet, what do we call a body that is just as big, or bigger, following a similar kind of orbit? Was the solar system suddenly full of new planets, hidden in the data like pebbles in snow? Or had our definition been too narrow all along? By the early years of the new millennium, it was clear that the old, simple list of planets could not easily accommodate this growing family of icy worlds. Astronomers, who are often both careful and stubborn, found themselves debating not just the properties of distant objects, but the meaning of the word planet itself. This was not a cold, abstract argument. It was emotional at times, reaching beyond observatories and scientific meetings into news headlines, classrooms, and casual conversations. Pluto had lived in people's imaginations for generations. Changing its status felt, to many, like rewriting a small piece of childhood. In the year 2006, the International Astronomical Union, the body that oversees the naming and classification of celestial objects, took on the difficult task of drawing a clearer line. After much discussion, they decided that, to be called a planet, a body in our solar system must satisfy 3 conditions. It must orbit the Sun. It must be massive enough for its own gravity to pull it into a roughly round shape, and it must have cleared its orbital neighborhood of other debris. Pluto met the first 2 conditions, but not the third. It shares its region with many other Kuiper Belt objects. And so, with a few careful sentences, Pluto was reclassified as a dwarf planet. The decision did not change Pluto's physical reality, of course. Its mountains remained mountains. Its nitrogen plains remained plains. Its thin, blue-tinted atmosphere still breathed in and out with the seasons of its long year. But the label on the chart shifted, and with it, we were reminded that science is not just a catalogue of facts, it is a living process. one that must occasionally revise its own language to keep up with what it has learned. Amid this debate, while people argued about names and categories, another, quieter mystery was emerging from the data. As astronomers mapped the orbits of distant Kuiper Belt objects, they noticed that some of them behaved in unexpected ways. Their paths around the Sun were not scattered randomly, as one might expect from a population of bodies jostled by billions of years of gravitational nudges. Instead, a subset of these trans-Neptunian objects seemed to share a pattern. Their orbits were elongated in similar directions and tilted in related ways, as though something large and unseen were gently shepherding them from afar. One of the first hints came from the strange path of Sedna, an object that travels on an enormous, stretched orbit that carries it far beyond the main Kuiper Belt. Others followed, each with its own lonely, distant ellipse. A particular group of these bodies, sometimes called detached trans-Neptunian objects, do not come close enough to Neptune for its gravity to explain their current orbits. Their paths seem to float just outside the range where Neptune can significantly disturb them. Even more extreme are the so-called extreme trans-Neptunian objects, whose elongated orbits carry them to staggering distances from the Sun, yet whose clustering suggests they are not simply wandering at random. It was as if the outer solar system's faintest members were tracing out the outline of something that was not visible, a gravitational sculptor working in darkness. To make sense of this, astronomers began to look for patterns more carefully. They measured the angles of these orbits, their distances of closest and farthest approach, and how their paths lined up with one another in space. Subtle groupings emerged, and alongside them, the possibility that these alignments were not a coincidence at all, but the footprint of an unseen planet. In 2014, two astronomers, Chad Trujillo and Scott Shepard, pointed out that several of these distant objects, including Sedna and another body known by the temporary label 2012 VP13, shared orbital characteristics that seemed unlikely to be purely chance. They proposed that an unknown planet, orbiting the Sun at perhaps a few hundred astronomical units distance, could be shaping these paths. Their suggestion was cautious, but bold. Maybe there was a large world out there, on a distant, nearly circular orbit, somewhere between roughly 200 and 300 astronomical units from the Sun, whose gravity was quietly guiding the dance of these icy wanderers. Their idea did not stand still. A couple of years later, in 2016, astronomers Mike Brown and Konstantin Batygin revisited the puzzle with fresh eyes and more extensive modeling. They examined the orbits of the most distant known trans-Neptunian objects, exploring whether a single, massive, unseen planet could account for the way these bodies seem to cluster in space. Using detailed computer simulations, they tested different scenarios, varying the mass of the hypothetical planet, the shape and orientation of its orbit, and its distance from the Sunday. Gradually, a picture emerged from these simulations. If there existed a planet several times more massive than Earth, on a long, elongated orbit tilted with respect to the rest of the solar system, many of the observed anomalies could be explained. The orbits of detached and extreme trans-Neptunian objects would be shepherded into roughly aligned configurations, their paths corralled by the distant planet's steady tug. At first, this world, Planet 9, as it came to be called, was thought to have a mass around 10 times that of Earth. As the models were refined, that estimate softened, settling into a range of roughly 5 to 6 Earth masses. That is still substantial, enough for Planet 9, if it exists, to be an ice giant of its own, perhaps somewhat smaller than Uranus or Neptune. but still powerful enough to rearrange the architecture of the outer solar system over billions of years. And yet, at such incredible distances, it would shine only faintly, reflecting very little sunlight. Even our best telescopes, scanning wide swaths of the sky, might easily miss it unless they happen to look in exactly the right place. The idea of Planet 9 is not just about adding another dot to the chart. It is about understanding why the distant outskirts of the solar system look the way they do. The hypothesized planet's influence would reach far beyond its immediate surroundings, helping to explain why certain trans-Neptunian objects have orbits that bunch together instead of pointing in all directions. It might also account for subtle tilts in the overall plane of the solar system, and the strange distribution of some high-inclination objects that move at steep angles compared with the main planetary disk. As word of the Planet 9 hypothesis spread, astronomers around the world joined the quiet hunt. Some searched existing survey images, combing through deep, wide fields of stars in case the elusive planet had already been accidentally photographed as a faint, slow-moving point. Others used powerful telescopes to scan likely regions of the sky, guided by the simulations that suggested where such a world might most plausibly be found. Meanwhile, theorists continued to refine the models, asking how Planet 9 might have formed, how it could have been scattered into such a distant orbit, and how its presence would have shaped the behavior of comets and smaller bodies over time. Nothing definitive has appeared yet. No single image with a clear, undeniable dot that moves against the background of stars in just the right way. The sky is vast, and a cold, dim planet on a distant, multi-thousand-year orbit would be a subtle thing to spot. But the search itself has deepened our understanding by tracing the orbits of distant objects with ever greater precision. Astronomers are learning more about the structure of the Kuiper Belt, the supply lines of comets, and the long-range gravitational tides that tug at the solar system from both within and beyond. In the tranquil balance of the inner planets, where Earth circles the Sun with familiar regularity, it is easy to imagine that our neighborhood is complete, yet far beyond. At the edges where sunlight fades to a pale whisper, the evidence hints that the story is still unfinished. Whether Planet 9 exists as a real, distant world, or whether the anomalies can ultimately be explained in some other way, the mystery has already done something precious. It has reminded us that even in a time of detailed maps and space probes, the cosmos around us still holds unsolved questions. For many people following these developments from afar, there is a kind of comfort in this ongoing search. It means that the solar system, which once seemed so neatly defined in classroom posters and textbook diagrams, is still alive as a place of discovery. Children who grew up reciting a list of 9 planets now watch as that list bends and flexes, making room for new ideas, new categories, and perhaps one day, a new, distant world that has been there all along, waiting for our instruments to become sensitive enough and our curiosity patient enough to finally notice it. In late-night observatories and remote mountaintop domes, astronomers continue to take long exposures of seemingly empty starfields, trusting that buried somewhere in those images might be the faintest trace of Planet 9 or of some other unanticipated surprise. It is slow work, and it may lead us in directions we do not yet suspect. But like so much of astronomy, the value lies not only in the answer we hope to find, but in the deepened attention we give to the sky while we search. Somewhere in that darkness, there may be a silent participant in the solar system's ancient dance, felt but not yet seen. And as telescopes grow more sensitive and surveys more complete, we continue to listen for the faintest sign of its presence, like waiting for a distant footstep in a quiet house at night, patient and alert, knowing that the unknown is still out there, just beyond the reach of our current light. From the hints and whispers of distant orbits, the search for Planet 9 unfolds like a very slow, very patient kind of story. No one expects an easy discovery. If this world exists, it is not a bright jewel hanging in the sky, but a shadow moving at the farthest edge of the sun's reach, where even sunlight seems tired by the time it arrives. The difficulty begins with distance. Planet 9, if it is truly out there, is thought to follow a huge, stretched-out path around the sun, an orbit so vast and elongated that it would carry the planet through regions where the sun is little more than a pale star among many. Out there, the light that reaches its surface is incredibly weak. What little sunlight falls on it is reflected back towards space as a faint glimmer, easily drowned out by the glitter of distant stars and by the soft glow of countless background galaxies. The planet itself would also be extremely cold, its surface locked in deep freeze. At such temperatures, it would emit only the barest murmur of thermal radiation, a whisper in the infrared that our instruments must strain to hear. This makes Planet 9 a master of hiding. Visible light does not catch it easily. Infrared surveys, which are powerful tools for finding cold, dim bodies, struggle as well, because there is so little heat to detect and so much noise in the sky. Starlight flickers, cosmic rays paint streaks on detectors, dust and faint galaxies clutter the background. Instrumental quirks and electronic static add their own quiet confusion. Amid all this, the signal from a single distant planet would be like a candle seen from across an ocean, its glow nearly lost in the shimmer of waves and the reflections of faraway shores. The challenge is made even harder by the sheer size of the search area. We do not yet know exactly where Planet 9 might be along its long, slow orbit. Our models, as careful as they are, can only narrow the possibilities to a broad swath of sky. Somewhere in that enormous patch may be one faint point that moves more slowly than the rest. To search such an expanse in detail, astronomers must carefully map it with wide-field telescopes, taking deep images and returning again and again to the same regions to look for anything that shifts position over time. It is like looking for a single grain of sand that has rolled slightly between one tide and the next. Then there is the matter of time. Because Planet 9's orbit is thought to span thousands of years, its motion against the background stars would be incredibly slow. From our vantage point on Earth, even after a decade, its position in the sky might change, only by a tiny amount, far less than the motion of the nearer planets we are used to tracking. Traditional methods of discovery, like watching for a planet's rapid march across the constellations, or waiting for it to pass in front of a star and briefly dim its light, are nearly useless in this case. Planet 9 would not obligingly parade across the sky or transit a convenient star on human timescales. It is more like a distant ship on the horizon of a vast sea, so far away that, to the naked eye, it seems almost motionless. Despite all of this, astronomers have not given up. If anything, the difficulty has sharpened their creativity. Large ground-based telescopes now use advanced adaptive optics, systems that subtly bend their mirrors in real time to counter the blurring effects of Earth's atmosphere. A bright reference star, or an artificial star, created by shining a laser into the upper air, provides a guide for these corrections. The result is an image that is crisper and more detailed than the sky would normally allow, opening a clearer window onto the faint and the far. In space, Observatories orbiting high above the air's turbulence stare steadily at chosen fields, gathering light for long stretches of time without the twinkle that distorts images taken from the ground. Future space telescopes, with wide cameras and sensitive detectors that can see deep into the infrared, are being designed with surveys of the outer solar system in mind. For them, Planet 9 would still be a challenge, but one that sits just a little closer to possibility. In the search for this hidden world, these tools are used in slow, systematic campaigns. Wide regions of sky are imaged, then imaged again months or years later. Astronomers compare these deep pictures, blinking them back and forth, much like Clyde Tombaugh once did with photographic plates when he discovered Pluto. But now the fields are larger, the stars more numerous, the exposures deeper, and the computers far more tireless. Software helps to sift through millions of points of light, flagging any that shift position just enough to be suspicious, while human eyes check the most promising candidates with a mixture of caution and quiet hope. Even with such methods, the search can feel like trying to find a needle in an astronomical haystack, except that the haystack is the sky and the needle may be dull, dark, and barely larger than a grain of dust in our view. So, researchers have begun to think more about indirect ways to sense Planet 9's presence, not by seeing it directly, but by noticing how it tugs on other things. One promising idea is to look not for the planet itself, but for possible moons that might circle it. If Planet 9 is several times more massive than Earth, it is quite reasonable to imagine that it could host one or more satellites. These moons, locked in orbit around their distant parent, would feel powerful tides as they slowly move through Planet 9's gravitational field. The constant stretching and squeezing of their interiors, tidal flexing, would generate heat, warming them from the inside out. We see this kind of tidal heating closer to home. Jupiter's moon Io is racked by volcanic activity because it is constantly pulled and twisted by Jupiter and its neighboring moons. Europa and Enceladus, moons of Jupiter and Saturn, are believed to harbor subsurface oceans of liquid water beneath their icy crusts, kept from freezing solid by the same tidal forces. Inside those oceans, hydrothermal vents and chemical gradients might provide energy sources that last far longer than surface sunlight ever could. In these environments, some scientists think the ingredients for life may quietly assemble and evolve in the dark. If Planet 9 has moons that experience similar tidal heating, those moons might be warmer than the planet itself, warm enough, perhaps, to emit more infrared radiation than their parent, making them slightly easier to spot with sensitive telescopes that look for heat instead of reflected light. In this way, a glowing moon could betray the presence of the hidden world it circles, like a small lantern revealing the existence of a traveler in the dark. Another innovative approach turns attention to visitors from beyond the solar system, interstellar asteroids and comets that occasionally pass through our neighborhood before heading back out into the galaxy. These objects move at high speed on hyperbolic paths, not bound to the sun, cutting through the outer regions where Planet 9 might lurk. In theory, if one of these interstellar wanderers passed relatively close to Planet 9, its trajectory would be ever so slightly bent by the planet's gravity. By tracking such objects with extreme precision, recording their positions over months and years, astronomers can look for tiny deviations from the paths predicted by models that include only the known planets and the Sunday. Any unexplained deflection, however small, might hint at a hidden mass nearby. This method is delicate and demanding. It requires not just excellent data, but also a careful accounting of every other gravitational influence along the way. Still, it offers a way to let Planet 9 reveal itself as a subtle sculptor of motion, rather than as a point of light. The same principle can be applied to spacecraft. When robotic explorers travel through the outer solar system, their courses are tracked with exquisite accuracy, using radio signals sent between Earth and the spacecraft. Even the tiniest change in their velocity or direction can be measured over time. If a spacecraft's trajectory were nudged by an unseen planet's gravity, that nudge could, in principle, be detected as a small but persistent discrepancy between the planned path and the actual one. In the past, hints of unexpected accelerations in spacecraft data have sometimes led to speculation about unknown forces or objects. Most of these anomalies have turned out to have more mundane explanations. Thermal radiation from the spacecraft itself, slight miscalculations, subtle engineering effects. But the technique remains powerful. With enough missions traveling through the outer regions, and with careful analysis, the collective data could help confirm or rule out certain possible locations and masses for Planet 9. It is a little like watching how leaves float on the surface of a hidden current. By studying their drift, you can map the water's flow without ever seeing it directly. There is a long tradition in astronomy of using such indirect clues to find unseen worlds. Neptune itself was discovered not by direct observation at first, but by noticing irregularities in Uranus's orbit and calculating where another planet would have to be in order to cause them. Planet 9, if it exists, would be a spiritual descendant of that same method. A world first glimpsed in equations and simulations, its presence inferred from gentle tugs on smaller bodies at the edge of the sun's domain. All of these indirect strategies share a common theme. Instead of staring into the dark and hoping to see the planet itself, they look for the wake it leaves behind. Planet 9, if it exists, cannot help but tug on other things: moons, comets, asteroids, spacecraft, even the orbits of distant trans-Neptunian objects. Its gravity is a silent, persistent presence. By mapping that presence with care, astronomers might one day narrow the search to a small enough patch of sky that a direct observation becomes possible. Until then, the search is a lesson in humility and patience. It reminds us how small our instruments are compared to the scale of the cosmos, and how even within our own solar system, there may be major pieces still missing from the puzzle. It asks us to accept that not knowing is not a failure, but a stage in the process of discovery, a pause between questions and answers. Yet it is also a testament to our creativity. Faced with a world that hides at the limits of visibility, we respond not with frustration alone, but with new techniques, new ways of listening, new questions to ask of the sky. This slow pursuit weaves itself quietly into human lives. Graduate students grow into seasoned researchers while the search goes on. Telescopes are upgraded, retired, replaced. New instruments come online, offering sharper views and deeper reaches. And with each improvement, the possible hiding places for Planet 9 shrink by just a little. What was once the whole sky becomes a wide band. What was once a wide band becomes a narrow strip. What was once a narrow strip becomes a handful of promising fields. Some night, perhaps in the not-so-distant future, a sequence of images will come in from a telescope. Maybe on a high, dry mountain. Maybe orbiting far above the atmosphere. On the screen, amid countless stars, one faint point will be seen to shift just a little between one observation and the next. It will move too slowly to be a nearby asteroid, too steadily to be a mere noise artifact. Checked and rechecked, its motion will hold. Orbital calculations will be made. Its distance will be estimated. Its path will be traced back and forward in time. On that quiet night, Planet 9, if it is real, will step out of theory and into sight, turning from a ghostly influence into a world with a position, a brightness, and, eventually, a story of its own. In the years that follow, more telescopes will turn toward it. Its color will be measured. Its size and mass will be refined. Perhaps, someday far in the future, a spacecraft will be sent to pay it a visit, repeating on a new stage the long, patient arcs once flown by the Voyagers and by New Horizons. Until that moment, the search continues, stretching over years and careers, carried forward by people who are willing to spend their nights looking into the almost invisible margins of the sky, trusting that somewhere out there, in the thin light, beyond Neptune and Pluto and the Kuiper Belt, a hidden planet may still be waiting to be seen. Out in the dark where our maps grow thin, the search for Planet 9 has begun to blur into something larger than a simple hunt for a distant world. When you look for something you cannot yet see, your mind naturally begins to wander through possibilities, some familiar, some almost wild. Astronomers, lying awake under their own mental skies, have not only imagined Planet 9 as a cold, distant planet, but have also wondered whether it might be something stranger altogether. One bold idea suggests that Planet 9 might not be a planet in the usual sense at all, but a primordial black hole, a tiny, incredibly dense remnant from the very early universe. Unlike the black holes formed when massive stars collapse, primordial black holes are hypothesized to have been born in the intense, uneven conditions just after the Big Bang, when the universe was still unimaginably hot and dense. In those first moments, slight variations in density could, in theory, have made small regions so heavy that they collapsed directly into black holes. If such objects exist, they might be astonishingly compact. A primordial black hole with the mass of a planet could be no bigger than a city, or even, in some theoretical estimates, only about the size of a basketball. It would be utterly dark, swallowing light rather than reflecting it. From far away, it would be invisible in any ordinary sense, yet its gravity would be as real and insistent as that of any world. In this picture, the clustering of distant trans-Neptunian objects, their strange, aligned orbits, could be explained by a black hole wandering through the outskirts of our solar system, a small, ancient knot in the fabric of space-time, tugging on icy bodies as it passes near. The thought is startling, almost unsettling. Instead of a remote, frozen planet with a surface you could, in principle, stand on, we would be dealing with a tiny, invisible pit in space-time. An object you could never land on or see directly, only sense through its pull. Yet it is also strangely elegant. No need for a faint, hard-to-spot planet if a compact, non-luminous object could play the same gravitational role. Another speculative idea goes even further from the familiar. Some researchers have wondered whether Planet 9, instead of being ordinary matter, could be a clump of dark matter, a compact concentration of the mysterious substance that does not emit, absorb, or reflect light, yet seems to make up a large fraction of the universe's total mass. Dark matter announces itself only through gravity. It shapes the motions of stars and galaxies, bends the paths of light in gravitational lensing, and helps hold galaxy clusters together. But what dark matter actually is remains one of the deepest open questions in physics. In the early universe, as it expanded and cooled, small fluctuations in density could have grown into structures of dark matter, clouds, filaments, halos. We believe that enormous halos of dark matter cradle entire galaxies, including our own Milky Way. On smaller scales, it is conceivable that denser knots of dark matter might exist, compact clumps that are hard to detect because they do not shine, yet still have enough mass to tug on nearby objects. If Planet 9 were such a dark matter clump, it could explain the gravitational anomalies observed in the outer solar system without requiring a visible planet. It would be, in effect, a ghost of mass, exerting force, shaping orbits, but remaining completely unseen in any conventional telescope. Only through its influence on the paths of icy objects and perhaps on passing spacecraft or interstellar visitors would it betray its presence. These possibilities, the primordial black hole, the dense dark matter clump, sound like something from a science fiction tale, whispered late at night. And yet they arise not from fantasy, but from attempts to harmonize what we observe with theories about the early universe and its unseen ingredients. They represent the outer edges of our imagination, tested against the rules of physics as we currently understand them. Most astronomers still lean toward the simpler interpretation that Planet 9, if it exists, is probably an ordinary, if distant, planet. But even entertaining these stranger ideas reveals how the search stretches our thinking. What they all have in common is this: whether Planet 9 is a planet, a black hole, a dark matter clump, or something else entirely, finding it or ruling it out would teach us something profound. We would either add a new member to the solar system's family, discover an exotic kind of object in our own cosmic backyard, or refine our theories so that the observed orbits of trans-Neptunian objects can be explained without such a visitor. In every case, we would come away with a deeper understanding of how the outer solar system is built and how the universe behaves on large scales. While these ideas swirl in the background, the practical work of searching goes on in a more grounded way. Recently, some of the loudest voices behind the Planet 9 hypothesis, Mike Brown and Konstantin Batygin, together with their colleague Matthew Holman, turned their attention to an enormous trove of observational data collected by the Pan-STARRS-1 survey. Pan-STARRS-1 is a wide-field telescope system that has spent years scanning the sky from a mountaintop in Hawaii, gathering deep images across vast swaths of the celestial sphere. On the first day of February of the year 2024, a preprint appeared describing their efforts. Instead of simply staring at where they thought Planet 9 might be, the researchers used the Pan-STARRS-1 archive in a clever way. The survey had detected billions of transient objects, points of light, that appeared on single nights and then vanished from immediate view. Most of these were things like asteroids, comets, variable stars, and noise. Hidden among them, in principle, could be faint glimpses of a slowly moving, distant planet taken at widely separated times. To pick this out from the chaos, the team used a sophisticated orbit-linking algorithm, something like a mathematical detective with a very patient eye. The algorithm looked for sets of detections that, when combined, could lie along the path of a single object moving under the sun's gravity. It is a bit like gathering footprints from different parts of a forest and realizing that, together, they trace the path of one animal rather than many. This process, sorting through billions of detections, checking combinations, rejecting false matches, is akin to searching for a single grain of sand in all the dunes along the entire coastline of North America. The work built on earlier wide-field surveys, such as the Zwicky Transient Facility and the Dark Energy Survey, both of which had already narrowed the possibilities for where Planet 9 might hide. Pan-STARRS-1 pushed this effort further, adding its own deep and wide coverage of the northern sky. Despite all this, no compelling candidate for Planet 9 emerged from the data. There was no faint point whose behavior matched the expected motion of a distant, massive body on a long orbit. At first glance, that might sound disappointing, like going to the attic to look for a lost keepsake and coming back with empty hands. But in science, a careful no can be as valuable as a yes. The Pan-STARRS 1 search allowed the team to rule out large portions of the parameter space where Planet 9 could have plausibly been located. By not finding the planet in regions where the survey was sensitive, they effectively said, if Planet 9 is real, it is almost certainly not here, nor here, nor here. In numbers, their results excluded about 78% of the possible combinations of brightness and position consistent with the most likely models for Planet 9. What remains is roughly 22% of parameter space regions of sky and ranges of brightness that were not well covered by Pan-STARRS 1, or where current data are not yet sensitive enough. These remaining patches are not failures. They are the next targets. They represent the frontier where our telescopes have not yet looked deeply enough or often enough to confidently say what is there. The search, then, becomes more focused. Instead of scanning the entire sky at random, future efforts can concentrate on these unexplored corners. Like a lantern moving slowly through a dark room, each careful survey lights up another patch of floor, and bit by bit, there are fewer places left where something large can hide. On the horizon of this ongoing work stands a new observatory with a wide, patient gaze, the Vera C. Rubin Observatory in Chile. When it begins its full operations, it will conduct what is called the Legacy Survey of Space and Time, a decade-long project that will repeatedly image the southern sky in remarkable detail. Night after night, year after year, it will gather a vast movie of the heavens, not just a set of still photographs. In that movie, asteroids will crawl, comets will flare, supernovae will blink into existence and fade, and perhaps, in the very slowest of motions, a distant Planet 9 will inch its way across the stars. The Rubin Observatory's powerful camera and wide field of view are especially well suited to finding faint, slow-moving objects. It will be able to detect things that are far dimmer than what many current surveys can reach, and it will revisit the same patches of sky often enough to catch the barely perceptible motion of distant bodies over time. If Planet 9 lies within the parts of the sky that Rubin will watch, and if it has not been ruled out already by previous surveys, this observatory may finally have the sensitivity and coverage needed to reveal it. But even if Planet 9 remains elusive, the journey toward it continues to enrich our understanding in other ways. Every search that fails to find the planet still yields catalogs of new asteroids, new comets, new trans-Neptunian objects. It refines our models of the Kuiper Belt, improves our knowledge of the distribution of small bodies, and helps us understand how planetary systems behave at their edges. The algorithms developed to look for a faint, slow planet can be used to discover other subtle phenomena. The data pipelines, the software tools, the methods of handling huge volumes of information, these are all gifts that persist long after a particular hypothesis is tested. In this sense, the search for Planet 9 is not just about another world. It is about the way we reach out into the dark with our instruments and our minds, accepting that the universe is more complicated and more surprising than we can see from the comfort of a single planet. It is about learning to live with uncertainty while still moving forward, step by careful step. Some night, perhaps years from now, a new paper will quietly appear, or a team will stand in front of a set of screens, pointing to a faint dot that shifts just enough between exposures to be real. Or perhaps, after enough sky has been searched and enough data analyzed, astronomers will conclude that the gravitational anomalies can be explained without invoking a hidden giant at all. In both outcomes, there is a kind of grace. We either welcome a new member into the solar system's distant family, or we refine our understanding of how the existing members interact. For now, Planet 9 remains an open question, a gentle mystery at the edge of our cosmic neighborhood. Its possible faces: icy world, primordial black hole, dark matter knot, or nothing at all, float like faint lanterns in the mind. The true answer is still beyond the reach of our telescopes, but not beyond the reach of our curiosity. And so we keep watching. We build better instruments, write smarter algorithms, share data across continents, and stare into the dim outskirts of the solar system with patient eyes. Somewhere in that vastness, whether it holds a hidden planet or only the quiet drift of ice and rock, the universe is being itself, deep, old, and full of stories we have not yet learned to hear.